Hello everyone, welcome to the lecture 16 of topology. This is in continuation to the previous lecture, lecture number 15, in which we introduced normality and regularity. In this lecture, we'll discuss about some results based on regularity and normality, in particular subspaces of normality and regularity, and we'll introduce about completely regular spaces. Just to recall the definition of regularity and normality, a topological space X is said to be regular if for every closed set A and a point X outside A, there exist two open sets U and V such that U contains X and V contains A, whereas this U and V are disjoint. Here we have the topological space X. This topological space X is said to be regular if for every closed set A and a point outside it X, there exist two disjoint open sets U and V such that U contains X and V contains A. Similarly, a topological space X is said to be normal if for every pair of disjoint closed sets A and B, there exist two open sets U and V such that U contains A, V contains B, and U, V are disjoint. Here we have the topological space X. This topological space X is said to be normal if for every pair of disjoint closed sets A and B, there exist two open sets U and V such that U contains A, V contains B, whereas this U and V are disjoint. Now let us discuss about subspaces. Subspace of a regular space is always regular. Let X be a regular topological space and Y be a subspace of X. Here we have X, which is a regular topological space, and Y is a subspace of X. We have to prove that this Y is regular. To prove Y is regular, we have to prove for every closed set A and a point outside it, there must exist two disjoint open sets U and V, whereas U contains that point and V contains the closed set. Let us take a closed set here, A. Here we have a closed set A in Y. A is closed in Y in the subspace. And here we have a point X in Y which is outside A. Since A is closed in Y and Y is a subspace of X, we know that every closed set in the subspace is intersection of a closed set in the parent space with the subspace. That means since A is closed in Y and Y is a subspace of X, there exists a closed set C in X such that A is equal to C intersection Y. This A is closed in Y, so there exists a closed set C in X such that A is equal to C intersection Y. Now C is closed in X and this point X doesn't belongs to C. So now we have with us X as a regular topological space, whereas C is a closed set in X and X is a point in X which is not in C. So by regularity of X, there exist two open sets U and V such that X belongs to U and V contains A, whereas U and V are disjoint. So here we are getting U which is open in X containing X and V is an open set in X which contains the closed set C. We need a open set in Y which contains A and we need another disjoint open set in Y which contains X. Now by subspace topology, this open set U in X intersection Y is open in Y. So this said reason U intersection Y is a open set in Y which contains X. Similarly, this B is open in X. So B intersection Y. B intersection Y is open in Y. So now we have two disjoint open sets U intersection Y and B intersection Y, whereas U intersection Y contains X and B intersection Y contains A. So the subspace Y is regular. So from this we can say that subspace of a regular space is always regular. But subspace of a normal space need not be normal. Here we have an example. Let X be 4-point set ABCD and tau be the collection of subsets of X containing the whole space, empty set, set containing 2 points BD, set containing CD, singleton set D, and set containing BCD. Clearly this tau is a topology. Now let us consider this topological space. Here these are open sets in tau. Then the complement of these open sets are closed. So closed sets in X are whole space, empty set, set containing AC, set containing AB, set containing ABC, and the singleton set A. Since there doesn't exist any disjoint pair of closed sets, X is vacuously normal. Here we can see that here we don't have disjoint pair of closed sets. Here we have a closed set AC, here we have a closed set AB, they are not disjoint. Here we have AB, here we have ABC, they are not disjoint. So we don't have any pair of disjoint closed sets in this topological space. So we say that this space X is vacuously normal because we don't have any disjoint pair of closed sets which needs to be separated by two pair of disjoint open set. So this space is vacuously normal. Let Y is equal to BCD be a subset of X. Since Y is a subset of X, Y is having subspace topology on it. Now the subspace topology on Y is tau Y is equal to Y empty set, set containing BD, set containing CD, and the singleton set D. Since these are the open sets in the subspace topology, the complement of these sets are closed in Y. Now the closed sets in Y are Y empty set, the complement of BD is C, complement of CD is B, and complement of D is BC. Now here for disjoint closed set B and C, we can see that here B and C are two pair of disjoint closed sets. But for these two disjoint closed sets, we don't have two disjoint open sets which separates them, because here we have these open sets. But the open set containing C is CD and the open set which contains B is BD. But these two open sets are not disjoint. We cannot find any pair of disjoint open sets which separates these disjoint closed sets. So this space is not normal. So here what we have seen? We have seen that subspace of a normal space need not be normal because here X is normal whereas the subspace Y is not normal. The next result is closed subspace of a normal space is normal. We have seen that subspace of a normal space need not be normal, but a closed subspace of a normal space is normal. Here is an additional condition. The subspace needs to be closed in the parent space. Let X be a normal topological space and Y be a closed subset of X. Since Y is a subset of X, Y is having subspace topology on it. And the additional condition on Y is that Y is closed subset of X. We have to prove that this y is normal. To prove y is normal, let us take two disjoint closed sets in Y. Let A and B be two disjoint closed subsets of Y. Since Y is a subspace of X, there exists a closed set C in X such that A is equal to C intersection Y. Similarly, there exists another closed set D in X such that B is equal to D intersection Y. This we know from the subspace topology. If a set is closed in the subspace, then the closed set can be written as intersection of a closed set in X with Y. So here A and B are disjoint closed subsets of Y. Since these are closed subsets of Y, for this A we have a closed set in XC such that A is equal to C intersection Y. C is closed in X. Similarly, here D is closed in X and B is closed in Y because B is equal to D intersection Y. So here we have C and Y are two closed sets in X because here we have taken that Y is a closed subset of X. Y is a closed subset of X and C is also closed in X. So intersection of two closed set is closed in a topological space. So if C intersection Y is closed in X. Similarly, D intersection Y is also closed in X because Y is closed in X and D is a closed subset of X. Therefore, A and B are two disjoint closed sets in X. Here we have seen that C intersection Y is closed in X, D intersection Y is closed in X, and C intersection Y is our A, D intersection Y is our B. So A and B are two disjoint closed sets in X. We have X as a normal topological space. So by the normality of X, there exist two open sets U and V in X because X is normal such that U contains A, V contains B, and U, V are disjoint. Since U and V are disjoint open sets in X, U intersection Y, V intersection Y are two disjoint open sets in Y by subspace topology. Since this U intersection Y is open in Y which contains A and V intersection Y is a open set in Y which contains B and their intersection is empty, we have two disjoint open sets in Y. One of them contains the closed set A and the other open set contains B. So Y is normal. So we have proved that closed subspace of a normal space is normal, whereas subspace of a normal space need not be normal. Here we have another separation axiom, completely regular space. A topological space X is said to be completely regular if for every closed set A and a point X outside A, there exists a continuous function f from X to the closed interval 0, 1 such that f of X is equal to 0 and f of A is equal to A. Our observation is that every completely regular space is regular. So basically, in the case of regular spaces, we have seen that a space is said to be regular if for every closed set A and for every point X outside A, there exist two disjoint open set. One of those open set contains the point A and the other open set contains the subset A. But in case of completely regular spaces, for this closed set and the point outside it, there must exist a continuous function from the space to the closed interval 0, 1, whereas that continuous function takes the point 0 to one end of this interval 0 and the function takes the subset A to the other end, that is 1. So f of x is equal to 0 and f of a is equal to 1. Now we have to prove that every completely regular space is regular. Let us assume that X is a completely regular space. Now we have to prove this space is regular. Now to prove X is regular, let A be a closed set in X and X be a point outside A. By complete regularity of X, there exists a continuous function f from X to 0, 1 such that f of X is equal to 0 and f of A is equal to 1. Now the interval 0, 1 by 2, whereas it is closed at 0 and open at 1 by 2, is a open set in the subspace 0, 1. If we consider R as real line and the closed interval 0, 1 as a subspace of that, then this semi-open interval 0, 1 by 2 is a open set in this subspace 0, 1. Similarly, the semi-open interval 1 by 2 to 1, which is closed at 1, is a open set in the subspace 0, 1 closed interval. Because we can find out an open interval in R whose intersection with the closed interval 0, 1 gives us this set, this interval 0 to half. So here this semi-open interval 0, 1 by 2 is a open set in the closed interval 0, 1. Similarly, the semi-open interval 1 by 2 to 1 is a open set in the closed interval 0, 1. Since f is continuous, and we know that in case of a continuous function, inverse image of every open set is open. So here this 0, 1 by 2 semi-open interval is an open set in this 0, 1 closed interval. And f is a continuous function from x to 0, 1. Now we have an open set here. Inverse image of that open set is open in x. So f inverse 0, 1 by 2 is a open set in x which contains the point x, and f inverse 1 by 2 to 1 is an open set in x which contains A. So here we have written that f inverse 0, 1 by 2 contains x and f inverse 1 by 2, 1 contains A. We know that this interval 0 to 1 by 2, which is closed at 0 and open at 1 by 2, and 1 by 2 to 1, which is open at 1 by 2 and closed at 1, are two disjoint open sets in the closed interval 0, 1. Since f is a continuous function, f inverse of this open set and f inverse of the other open set are two disjoint open sets in X containing X and A respectively. Hence X is regular. So we have because we have taken a closed set A and a point X outside A, and we got two disjoint open set f inverse 0 to half and f inverse half to 1 separates X and A. Hence X is regular. So every completely regular space is regular. Now let us summarize what we have studied in this lecture and in the previous lecture. Every normal space need not be regular. The space discussed in example 4 of topology lecture 15 is a normal space which is not regular. Every completely regular space need not be normal. For that we can see the Sargent-Frey plane RL square is completely regular but not normal. This example is available in all topology book, Sargent-Frey plane. This is a very important example uh, which is completely regular but not normal. Every T1 normal space is regular. Proof of this statement is discussed in the topology lecture 15. Every housed-up space need not be regular. We have discussed K topology in the topology lecture 4. The K topology on real line is housed-up but not regular. Every regular space need not be housed-up. if we consider any infinite set with indiscrete topology, this is vacuously regular but not Hausdorff, because in any infinite set with indiscrete topology, it is vacuously irregular because in case of an indiscrete topology, the only open sets are the whole space and empty set. So closed sets are also empty set and whole space. So we cannot find a closed set and a point outside it in the case of an infinite set with indiscrete topology. So the space is vacuously regular, but the space is not housed up because for every pair of distinct points, we cannot find two disjoint open sets which separates them. So we have studied about normality and regularity. There are some more results of normality, regularity, and complete regularity related to compactness. So after studying connectedness and compactness, we'll again revisit this higher separation axioms.